Okay. And so this is our lesson 13, meaning it's the 13th time we've gathered together for lecture, but it corresponds with chapter 19, lesson 19 in the textbook, and it's about batteries. And so what I want you to do at the beginning of our time together, I want you to take about 90 seconds, work with those around you, and I want you to come up with a definition of a battery. I want you to define a battery, okay? Did I say 90 seconds? I think that's a good length of time. So you have 90 seconds starting now. What is a battery? You have about another 30 seconds. You don't need it? You know what a battery is? All right, what's a battery? This is our first framing question, by the way. What is a battery? What is a battery?
Is something that stores energy.
Something that stores energy. Okay, Tom?
Is it something that can reliably take in, store, and discharge electricity?
Something that can reliably take in, store, and discharge electricity. It's interesting. So most batteries are somewhat self-contained. So the taking in energy is interesting. We can recharge batteries in which you reverse them, but we'll get to there. That's not a bad definition. It's not a bad definition at all. I'm going to define a battery for you in such a way that's going to be frustrating because my definition of a battery is going to include two words that you probably don't know what they mean. Here we go. A battery is two or more voltaic cells connected in series to provide steady voltage. Two or more voltaic cells connected in series to provide steady voltage. And you're like, this is awesome. I love this definition, Dr. Engel, for several reasons. One, I like how long it is, because I always like definitions with a lot of words. And two, I really like that it includes words that I have no idea what they mean. Oh, this is good. So voltaic cells, a two or more voltaic cells connected in series to provide steady voltage. And so what questions do you have after reading this definition? What are some questions? What is a voltaic cell? And what is steady voltage, right? I'm glad you asked. First answer, a voltaic cell is made from metal electrodes immersed in an electrolyte. And so here we've got, some more terms you probably have not seen before. Electrode. I know you've seen electrolyte before. Right, we use this when we talk about Gatorade and Powerade, just packed full of electrolytes. Yes? So you've seen this before. You may not know how it applies to chemistry or what it actually means. But now we're starting to paint a picture of what a battery is. What a battery is. Okay, so you're like, okay, well, a battery is two or more voltaic cells connected in series. And now you know, okay, a voltaic cell is metal electrodes immersed in an electrolyte. And so here's a container. Here, I'm going to draw a battery for you. So I told you that my primary goal today is to make it to when you hear the term battery, you do not think like AA, AAA battery any longer. You think about the chemistry. Because this is what I want you to image in your mind. I want you to see battery and think voltaic cell. And this is a voltaic cell. So here is a container. Within this container is a liquid electrolyte. You see this? This liquid? I drew waves in there to show you that it's a liquid. There should not be waves in there because waves create forces and then batteries blow up. But I want you to know that this is a liquid. So here we have our electrolyte. An electrolyte it's a liquid that's either an acid or a base. Okay, it could be either. It could be an acid or it could be a base, and we're going to talk a lot about acids and bases next week. You're going to get your fill of a discussion of acids and bases. So for now, you hear electrolyte, you think fluid. But a voltaic cell is more than just an electrolyte. What is it? Metal electrodes immersed in an electrolyte. And these are electrodes. And so this is a voltaic cell. Electrodes immersed in an electrolyte. And then a battery is going to be at least two of these voltaic cells connected in series to provide a steady voltage. We're like, okay, so now I have an image in my mind of a voltaic cell, and I still don't know what voltage means. Here's the idea of voltage. So voltage is produced by separating charges as electrons move. So voltage is produced from the separation of charges as electrons move. Voltage is produced from the separation of charges as electrons move. Give you a minute to write that down, and then there's something else I want you to write down about this. Voltage is a type of potential energy. Okay, voltage is a type of potential energy. I want you to write that down. You can think of voltage as electrical potential energy. Electrical potential energy. What does potential mean? We usually use it as like a backhanded compliment. Right? Like when somebody's really messing up their lives, we're like, man, you had so much potential. Or even you have so much potential. Right? It's usually a way of saying, you're really not measuring up to what you ought to be. Right? You know what I'm saying? So potential energy then is what? It's not currently active energy, it's potential energy. Okay, so voltage is like this. It's electrical potential energy. Now it can turn into energy that's actually doing work, or it could just remain potential energy. Like you've got a battery with a voltage of 1.5 volts, which is basically every battery you've probably used in your life besides a few. Like the battery if you've got a phone or a tablet or a laptop computer has a different voltage, but AA, AAA, C batteries, D batteries, they've got a voltage of 1.5 volts. And if that battery just sits there, that is potential energy, that is not doing anything, right? You pick up that battery and it's not like something magical happens, right? And all of a sudden you feel energized. That'd be really nice if that's the way it worked, right? You just feeling a little like groggy, and instead of consuming caffeine, you stick a battery in your pocket, and all of a sudden you're energized. Yeah, it'd take a lot more than 1.5 volts to energize me. You guys are teenagers, so you're always either exhausted or unbelievably energized, right? There's really nothing in between. Life is not like that forever. As an encouragement. Okay. And so it can then be converted into actual electrical energy if that separation of charge encourages electrons to move. Because where are electrons going to want to go? What's the charge on an electron? Positive or negative? Negative. So where's an electron going to want to go?
Positive.
Where there's positive charge. Okay, so if we're maintaining this voltage, this separation of charges in a battery, and then you put this battery into something, allowing electrons to flow, they're going to flow to the positive terminal of the battery. And as those electrons move, you can harness that energy to do something. Like power the remote control for your car. Because if you can't power the remote control for the car, you can't chase your dog around the house with the remote control car, right? And then you're like, why does this remote control car even exist if I can't chase my dog around the house? If you ever chase your dog around the house with a remote control car, it's a horrible thing to do, but it is awesome. It is awesome. You just don't want to get too close, especially if your dog has long fur, and get it caught up in the wheels of the remote control car, because then the car's stuck to the dog and then can't chase it. It's actually part of the dog now. All right? So, what is a battery? I would like for you to answer this question by drawing this picture. If you haven't already drawn this picture, you should draw this picture right in the position where you put the answer to your questions. And so if you only have a small amount of space, which you probably do, draw this small. But again, I want you to hear battery and think voltaic cell. And I want you to think voltaic cell and picture this. 2 metal electrodes suspended in an electrolyte. That's what I want. Is that what I'm going to get? Maybe. But that's the image I want in your mind when you hear battery. Because this is what is inside of the batteries that you're using to power your remote for your remote control car. Okay. All right, any questions? A couple of key terms. I would like for you to look up voltaic cell right here. Voltaic cell, and look up voltage. There's some other terms there that you can look up if you want as well. You can look up electrode and electrolyte, but you don't need to. Any questions about this question? What is a battery? Okay, so again, this is what I want you to see when you see battery. Joe.
Is it different with the lithium battery?
Lithium-ion batteries are still constructed like this, but they're a little bit different than some other types of batteries. But yeah, lithium-ion batteries still have chemistry like this. Electrodes suspended in an electrolyte. Lithium-ion batteries are kept under an enormously high pressure. And so lithium-ion batteries can be really dangerous if they fail. Because they can fail catastrophically. Which is so cool because we power devices that we put in people's bodies with lithium-ion batteries. But we're pretty good at making batteries. We're pretty good at making batteries. I'm not very good at making batteries, but the people that make batteries are pretty good at it. So how do we build batteries? Because we're like, okay, now you're like, okay, I hear battery, I see this. It's going to take a lot of work to erase when you close your eyes and hear battery, seeing a AA battery. It's going to take a lot of work. I understand that, but I'm ready to work. Ready to work to where when you hear battery, you see this. But how do we actually build this? And so here is this drawing up here. But notice there's something on here that is not on here, and that's some signs of the charge. Okay? So let's build this. Let's build a battery. Let's build a voltaic cell. Shall we? First thing we do is we set up a negative terminal. So one of the cathodes, ignore what I just said. Cathode, ignore that for a minute. One of the electrodes we place into this electrolyte is going to be our negative terminal, what we call our anode. Okay? It's going to be our negative terminal. And you're like, okay, well, how do I know how to set up a negative terminal? Right? You're like, I'm all in, Dr. Ingall. I'm going to build a battery. I'm going to get myself an electrolyte that I know is either an acid or a base. And you're like, I know where I can get an acid. I'm going to go to my cupboard. I'm going to get some vinegar. Right? And so I need to know, how do I set up this negative terminal? I'm glad you asked. You take something that forms positive ions. So you take something, you put it into the electrolyte, and that something needs to be a material that forms positive ions. And you're like, now we're going to start applying some of the chemistry I've been learning. What types of elements make positive ions? Metals. Those that are on the left side of our periodic table, because they give away electrons to get what every atom wants, and we know that every atom wants a completely filled outer energy level, right? Metals give away electrons to make that happen. So which means, what are we going to suspend in the electrolyte to make our negative terminal, our anode?
Metal.
A metal. And you're like, okay, I think I can accomplish this, right? I chew gum, and I've got this aluminum foil wrapper. I'm gonna make myself a little negative terminal, and I'm gonna suspend it in this vinegar. But then so this facilitates an oxidation reduction reaction. We've talked about this reaction before. Oxidation reduction reaction, or a reduction reaction, it's the transfer of electrons, right? Do you remember do we call it an acronym? No, a mnemonic. There we go. Do you remember the mnemonic I taught you for oxidation reduction reactions? Do you remember it now? Oil rig? No? This isn't, maybe I didn't teach you this.
I think in biology.
Oh, okay. So this stands for oxidation is loss. Reduction is what?
Gain.
Is gain. Man, that's critical thinking right there. Well done. So oxidation is loss, reduction is gain. And gain of what? If we're forming positive ions, what are we losing? We're losing electrons, right? In order to become a positive ion, you have to lose electrons. Yes? So the anode is losing electrons or becoming oxidized. You see that? The anode is losing electrons, is being oxidized. The electrolyte is gaining electrons and being reduced. Because if something's oxidized, something has to be reduced. We've talked about this before. You can't just expel electrons. If you want to get rid of electrons, you got to find something to take them. Right? Okay. There's nowhere to put them. There's no like electron garbage can. Okay? If you don't want your electrons, you got to find something to take it. You're like, cool. We've got a negative terminal. But what else do we need, according to our picture? We need a positive terminal. So then we set up a positive terminal. We call this the cathode. Set up a positive terminal called the cathode. And now we have built a battery. We put an anode in that's going to form positive ions, meaning it's going to get rid of what? How do you it's going to get rid of electrons. Now it gets rid of them by giving them to something else, but it's going to get rid of electrons, meaning our anode is our electron source. On your worksheet for lesson 19, do you see the matching? Go ahead and pull out your worksheet. I'm going to give you one of these answers. For number 2, it says source of electrons. What is our source of electrons? Our anode, letter A. And you're like, that's so cool. But you're like, where are those electrons going to go? they're going to go to where it's positively charged. We just stuck a positive terminal into here called what?
Cathode.
The cathode. So we've got another one here, number 3, that says accepts electrons. What accepts electrons? The cathode. But the beauty is, if we design this battery in such a way that the electrons can only get to here if they move through your circuit, this battery can now power your device. Okay, because the electrons want to leave here, but if the only way they can get from here to here is to go through in a wire, now you can use those electrons moving to power a device. Have any of you ever seen a YouTube video where they charged an iPhone with oranges? It's amazing. Because the beauty of oranges is oranges are full of citric acid. And an acid or a base is going to be an electrolyte. So it's a voltaic cell waiting to happen. All you have to do is stick into that orange an anode, a metal that's going to donate electrons, and you stick somewhere else in the orange a cathode, and you make it to where the only way they can transfer is through a wire connecting the two. If we link a whole bunch of oranges together, I think it took them 500 and something oranges. I don't remember the number. But they linked these all together to get enough voltage to charge an iPhone. That's pretty cool, right? I mean, anything acidic is just it's a voltaic cell waiting to happen. You're like, well, Dr. Engel, you said it could be basic too. And that's right. You're like, so is like Drano, is that just a battery waiting to happen? And the answer is yes. Stick an anode and a cathode in there and you've got yourself a battery. But Drano's also extremely basic and it's dangerous, which is how it, dissolves things inside of drains. So not a good idea to build batteries out of Drano, but you could. All right. So how do we build batteries? What I'd like for you to do here is just to write C, my previous picture. C, S-E-E, my previous picture. That way you get dual use out of that picture you drew. You used it to answer that first question and you used it to answer the second question. Dual use. Call that multitasking or dual use. Either way, you're welcome. All right, what types of batteries exist? Now, usually our lectures only have 3 framing questions. This one has 5. So you're like, oh, wow, we're already on the 3rd one and it's only 1:40. We're going to get out of here early. You are not getting out of here early. Not going to happen. I mean, if you want to leave, you can just get up and walk away. You're not trapped in here. Some of you were trapped outside when the door closed, but... What types of batteries exist? We can basically put batteries into one of 2 categories. And we do it based on whether or not they can be recharged. So the first type of battery, called a primary cell. These cannot be recharged because the chemical reaction, the anode giving up electrons, the cathode accepting those electrons, it's irreversible. You cannot restore that reaction to its original state. It is irreversible. Once it's gone, it's gone. During your lifetime, you will probably see the disappearance of traditional batteries. And I don't know if that'll be exciting for you, like the day that the last disposable battery, gets, recycled and gotten rid of, that you will celebrate. But that will probably happen during your lifetime. Tom?
So that was based on what metal you use in it? Right?
Well, yes. Yeah, I mean, the type of metal that you use is going to have a big impact on whether or not the reaction is reversible. Absolutely. Absolutely. Okay, so I'm going to give you a few examples of primary cells. First type, the carbon zinc cell. Zinc is the anode. The carbon zinc cell. Zinc is the anode. If zinc is the anode, what is it doing? Is it donating electrons or accepting electrons? It's donating electrons. And what type of elements donate electrons? Metals. So what do you think zinc is? It's a metal. Carbon is the cathode, which means that it's accepting electrons. And what types of elements accept electrons? Non-metals. Ooh. So that makes carbon a non-metal, and it is. It is a non-metal. Although we can build these in really complicated ways. All right. So this is a type of primary cell. Once zinc has given up its electrons, you cannot get it to take them back. Okay? Alkaline cells. Zinc is still the anode here, but you use potassium hydroxide as the electrolyte. And potassium hydroxide is a very, very strong base. And alkaline cells, they work a lot like carbon zinc cells, but they provide longer lasting voltage. The voltage, that potential energy, that separation of charges, it lasts longer. The zinc more slowly gives off its electrons. How do we know that potassium hydroxide is the electrolyte from the way that that phrase is phrased?
It's inside.
It's inside, right? It's saying zinc is the anode in potassium hydroxide. And you hear anode, you hear battery, you think voltaic cell, and you know that our anode and our cathode are suspended in our electrolyte. Right? Couple more primary cells. The zinc chloride battery. What do you think's the anode? Zinc, still the anode. You're like, wow, what is it about zinc that makes it such a wonderful anode? You're like, I bet zinc is really, really happy to get rid of electrons. One more type, the silver oxide battery. Notice what's still our anode. It's still the zinc. Zinc anode with a silver oxide cathode. So silver is a metal, but when we make this compound silver oxide, it is not a metal. It's a metal with a non-metal, and it forms something that is electron hungry. It works as a great cathode, the part that accepts electrons. Yeah, Josh.
What's the cathode of the alkaline cells?
Of the alkaline cells? It can be, yeah, that's a good question. Usually it's still carbon, but it can be a number of different materials. Yeah, that's a good question. And then chloride, of course, would be chlorine. That's the cathode there. Yeah, in alkaline cells, usually it's still carbon. That's the cathode. It's just a different electrolyte. Okay, so if one type of battery is called a primary cell that cannot be recharged, what do you think we call the type of battery that can be recharged? Secondary. Secondary cells can be recharged because the chemical reaction is reversible. The anode can be forced to take its electrons back. The anode can be forced to take its electrons back. Secondary cells can be recharged because the chemical reaction is reversible. Now, that statement is what you need to know about secondary cells. I'm going to give you some bonus information in case you want to know how do you build this type of battery. What you do is you use something very similar in your cathode to what's in your anode. Okay? You use something that's chemically similar, but one of them wants electrons and one of them will give electrons. But if they're chemically similar, to get them to move backwards is doable. Now, it requires an energy input to make it work backwards, right? If you're going to recharge a battery, how do you do it? You plug it in, right? And you provide electricity necessary, so it still requires energy to do it. But if they're chemically similar, we can get the electrons to move backwards. Now, I want you to think about a battery type that you know is going to be rechargeable. Tom, you already talked about it. When you asked about, was it you that asked about lithium ion batteries? Oh, that was Joe. I'm so sorry. Joe, you already talked about it. What type of battery can be recharged? A lithium ion. Great example of a secondary cell. And so the anode is lithium, and the cathode is chemically very similar. It's oftentimes lithium combined with something else. And so lithium anode donates electrons to something that also contains lithium. And then you can input energy to reverse that and make the lithium take its electrons back. Now, during the process, that anode is chemically changed. And so eventually you run out of opportunities to recharge it. If you notice that lithium ion batteries, after a few years, they don't hold a charge like they used to. You notice that? The main things that you use lithium ion batteries for, laptops, tablets, cell phones, pacemakers. You're like, I don't have a pacemaker. Maybe you do. I mean, everybody has a pacemaker. Most of us have a natural pacemaker, but sometimes you have to put a synthetic pacemaker in. But anyways, after a certain number of charges, these lose capacity and have to be replaced. All right, can you think of another battery type that can be recharged? Give you a hint. It's in a device that got you here today. A car battery. Okay, and so the car battery is also a secondary cell, and it's called a lead acid cell. A lead acid cell. The chemical symbol for lead is Pb. And yes, lead does not include a P or a B, but lead, I think in German, is pluvium, which is where this the chemical symbol comes from. So your anode is lead, and your cathode, look at this, is lead peroxide. Is chemically similar to the anode. So the lead is going to get oxidized, have electrons stripped away. The cathode is going to get reduced, but you can reverse this reaction. In fact, your alternator does this as your car is running. As your car is running, it takes energy from the burning of the gasoline to recharge this battery, to get lead to take its electrons back. But eventually, again, like all batteries, it loses its capacity, and eventually you have to replace your car battery, right? Did you know that you had to replace car batteries? Okay. Now, if you have an electric car, it's different. They don't have a lead acid cell. They have typically a lithium ion battery or something similar, if you've got a fully electric car. All right. So what types of batteries exist? How should we answer this question? C-list. S-E-E-L-I-S-T. Or you could write primary and secondary if you want to do that instead. If you're getting tired of writing the C list, you're like, Dr. Engel, it feels like I'm cheating. Like I'm plagiarizing myself. Do you know that oh, never mind, sorry. So I mentioned a few minutes ago that during your lifetime, you will probably see the disappearance of traditional batteries, both primary and secondary cells, to be replaced by what we call fuel cells. So the next question we're going to answer, this is question number 4. What are fuel cells? Fuel cells are not batteries. Okay? What are fuel cells? Again, these are not batteries. What are fuel cells? I'm glad you asked. This is what they are. Fuel cells are devices that convert chemicals into water and produce electricity in the process. So fuel cells are devices that convert chemicals into water and produce electricity in the process.
drinkable water? Or
It is drinkable water. Well, that's complicated because it actually is pure water, which is technically not drinkable. Like you're not supposed to drink distilled water because it thins your blood out too much, and then the extra water in your blood rushes into cells and starts blowing them up. But it is pure water, and if you mineralize it, you can drink it. But this is how they, you can't create energy, but this is how they produce energy and drinking water on the space station using fuel cells. They convert chemicals, specifically hydrogen and oxygen, into water, which provides energy necessary to run the space station and also provides pure water that can be mineralized to drink. You're like, that's so cool. That is so cool. And here's the beauty of a fuel cell. It never goes dead. As long as you continue to feed it oxygen and hydrogen, it will continue to convert them into water, producing energy and clean water. You're like, why don't we just use these all the time? Because they're really, really expensive. We're getting better at it and making them less and less expensive, but man, they are really expensive. Plus, it has to be very, very highly controlled because these release a lot of energy. They are very efficient. And you're like, that's so cool. We use these in some cars. There are cars with hydrogen fuel cells that burn hydrogen in the presence of oxygen to produce water and power the car. You're like, that's so cool. But it's a really powerful reaction. And so you have to very tightly control the amount of hydrogen that gets burned. Otherwise, explosions happen, which aren't great to happen in cars.
what cars?
Honda has a hydrogen fuel cell powered Civic, I believe, and Toyota has a hydrogen fuel cell powered, I think, Corolla. They're not super widely used because it's hard to find a place that dispenses hydrogen. Again, because it's complicated and you have to very tightly control the release of hydrogen. And so you get a leak at like a traditional gas station. I mean, it smells, and if you you lit a match, it might be dangerous. But you get a leak at a hydrogen fuel station, and you're begging for like a huge explosion. So,
What kind of battery does the Tesla use?
I believe the Teslas use a lithium ion battery. But I'll get that answer for you before we leave. Here, I'll get that answer for you right now.
So,
Yeah.
if they're planning on replacing all batteries with those,
We have to get better at it.
they won't be
Wait.
rechargeable unless you can find a way to.
Well, you just keep giving it more fuel with a fuel cell. So you just give it more fuel and just make more water.
I feel like it's gonna lead to a lot of places.
Yeah, it is a lithium ion battery.
They're just gonna be sending, like, you need to refuel recharge your batteries and stuff. It's gonna have like a package of pure,
Hydrogen that you can burn.
Inside your house.
Then some people just start blowing out for fun, and it's gonna be on fires and stuff. But
I don't know. But
Maybe, but those are some of the challenges that we have to overcome to do this. But they're way more efficient than traditional batteries, and they produce material that we need, right? We need water. I don't know if you knew this or not, but water is pretty important to life. So, I mean, yeah, there are some big challenges that we have to overcome. But overcoming them does something pretty incredible. All right. So that's it for that question. What are fuel cells? You could just write C first point. C first point. There's no need to write it out again. And that's it for that question. So I know there are 5, but that one was pretty short. I have one more question for you that we need to talk about, and it's this one. How can we get a higher voltage? So if we're using batteries to power a device and we want to get a higher voltage, how do we make that happen? Okay. So what I want you to do is this. I want you to take about 60 seconds. I gave you 90 seconds on the last one. You didn't use it. So I'll give you 60 seconds this time. Talk with those around you, and I want you to come up with a solution to this problem. You've got 1.5 volt batteries, and you have a device that requires 5 volts of potential to power it. What do you do? What do you do? And you're like, well, we just use a battery with a higher voltage. It's not an option. It's not an option. You have the tools that you're given, which are batteries with a 1.5 volt potential. Okay? How do you power a device that requires 5 volts of potential? Okay, 60 seconds. Starting now.
Does the screen kind of show you the answer?
It may.
It says 4.5 volts.
It sure does, and that sure looks like the sum of 3 batteries with a 1.5 volt potential. And so what do? You combine the batteries in series. You put one battery right after another. And so here we have 3 batteries that all have a potential of 1.5 volts. If we put them together in series, right, we take the positive terminus of one and we put it right up against the negative terminus of another, and do that for 3 batteries, we can sum their voltage. We can sum their potential. And if your device requires 5 volts, this still isn't quite enough, so you add a 4th battery in there. And you're like, now I have more voltage than I need, which we'll have to control another way, but you have enough. You'll have enough. And if you're like, well, how do you control if you have more voltage than you need? Those of you that have taken physics, you might remember the answer to that. You put a little device in called a resistor, which reduces voltage. Anyways, that's another story for another time, okay? And so you combine the batteries in series. Have you noticed that some remote controls require you to put the batteries in this way, in series? But other devices require you to put the batteries in a different way, that they're not in series, they're in what we call parallel. Combining batteries in parallel or side by side does not increase the voltage. Instead, what it does is it increases the capacity. It allows the voltage to last longer. And so combining the batteries in series again, that's going to increase the voltage. Combining the batteries in parallel does not increase the voltage. What it does is it maintains the same voltage, but it allows that voltage to last longer. Increases the capacity. And so, are you thinking this? Dr. Engel, does that mean if I have a remote control that has the batteries go in parallel, that I can power it with a single battery? And the answer is probably. But you'd have to trick the thing into thinking it had all of the batteries in there, and it would burn through that one battery very, very quickly. But you could probably power it with a single battery. But again, you'd have to trick the machine into thinking you had more batteries. You'd have to connect all the terminals inside of those positions with some wires. But you could probably get it to function because it only needs the voltage of a single battery. But it's going to burn through that battery very, very quickly. So.
Is there a reason why it always has in parallel things like positive here, negative here? Next one has a negative on top, positive on top.
Yeah. It helps to ensure that the batteries are not, well, so if it inverts them like that, they're in series. So if you're putting them side by side but they're inverted, they're still in series. They're all connected together. In order to be in parallel, they would all need to be oriented the same way. So they're side by side, but they're oriented all with the positive charges up. That's a good question. That's a really important clarification point. So if it requires you to put the batteries in side by side, but they're inverted, they're connecting them in series. And it's just designed to make that happen in as small a space as possible. Make sense? So you don't have to have, like if you've got a remote control that needs to sit in your hand, but you need to connect the batteries in series, this is a way you would do it. Yeah, that's a good point. That's an excellent question, Joe, and a really important point of clarification. Okay. Questions? Thoughts? How should we answer this question? How do we get a higher voltage?
Combine batteries in series.
Combine batteries in series, which is also the first point. So if you want to say C first point, although that's only one word less than just rewriting the first point again. Huh?
Asterisk.
Yeah, asterisk. Yeah, just put a little asterisk. You picked that up this morning. This is clever, right? Yeah, it's an excellent use of asterisks. All right. Well, if you haven't already done so, please get lessons 16, 17, 18, quiz over lesson 17, exam over lessons 13 through 16, and lab 4 ready to go and into your